Welcome back, everybody. This is our fourth session in JEE mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have covered three videos or made three videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So, if some of your friends are preparing for NEET, then you can guide them through those videos also. And if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount will be highly appreciated. So with this, let's start today's video. In the previous one, we completed around up to question 15. This was the last question which we completed. Now let's start with the next one. Let me adjust pen thickness. So in the coil of resistance 100 ohms, so resistance is given to us 100 ohm. Current is induced by changing the magnetic flux through it as shown in the figure. So we have to find out magnitude of change in flux through the coil. So we have to find out d phi or change in flux. Now we know that flux is given by, induced EMF, I can say. Induced EMF is given by d phi by dt. And now flux we know that is equal to dot product of magnetic field and area. In this question, neither we have magnetic field nor we have the area to calculate the flux. So we have to use some other method. Now, so we will use this equation. So here EMF is d phi by dt, and from this we can write that d phi is equal to E dt. So what we will do here, we will integrate the induced EMF. And again, we don't have the induced EMF, but we know that from the Ohm's law that V is equal to IR. So we can use this value. So d phi will become IR dt, and now we can integrate it. We substitute value of EMF is equal to IR, and now we can integrate it. So from this, here resistance is constant, I is variable, current is variable here. So integral d phi is equal to resistance I dt. So now we can solve it by two methods. First, as we have here we have a graph of current versus time. So what we can simply do, we can simply calculate the area of this graph, and that will be equal to the integral. So first the area method. So here phi will be r into area of idt graph, where we have current here and time here. So area of this graph will be half into base, that is 0.5 or 5 by 10, into height, that is 10. So that will be 5 by 2. Now resistance is 100 into 5 by 2. So this will be 50 or 250 Weber. That is the value of flux here. Or in the second method, what we can do here, we can form an equation of current from this graph. Let's see how we do it. What we can do, we can equation of current from this graph. We know that y is equal to mx plus c. This is a straight line equation. Here y is the current axis and x is the time axis. and c will be some constant. So we can say I is equal to slope. Now its slope will, we can calculate that slope will be, we have to take some 2 points. Suppose this is our initial point and this is our final point. So slope will be dy by dx, change in value of y by change in value of x. Now change in value of y will be 0 minus 10 and change in value of x will be zero point 0.5 minus 0 over zero point 0.5. So it will become out to be slope is minus 10 by 5 into 10, so minus 20. So minus 20 into time plus constants. Now what we can put value of this point. This point has a coordinate of 10, 0 comma 10. At this point value of time is 0 and value of current is 10. Then we will be able to find the value of constant. So current is 10 minus 20 into time is 0 plus c. So from this c comes out to be 10, and our equation becomes for current, that is minus 20t plus 10. That comes out to be our equation of current, or we can write it like 10 minus 20t. So this is the equation of current in terms of time. Now we can substitute this equation here. What we have, we already have that d phi is equal to r times I dt, and the value of I is this. So it will be 20 minus 10 minus 20t into dt, and limits of time will be 0 to 0 0.5 second. Time is varying from 0 to 0 0.5. So 0.5 is half, and value of r is 100. So phi is equal to 100 times 0 to half. Integral inside will be 10t minus 20t square by 2, or we can say 10t square. From this, now okay, this will be integral we have solved, so this will be limits only. So phi will be 100 into 10 of t into 1 minus t with limits 0 to half. If we put it 0, then all will be 0, so we will be only substituting t is equal to half. So it will be 1000 into half into 1 minus half, that is half. So 1000 by 4, that would be again 250 Weber. So via both methods, we get option A as the right answer. So whatever method you can choose. Next one, a conducting metal circular wire loop of radius r is placed perpendicular to magnetic field which varies with time. So there is a loop of radius r placed perpendicular to the magnetic field. I think here it is mentioned regarding the plane of the loop. Means if this is our loop, then this plane of the loop is perpendicular to magnetic field. So we have B here, and area vector of this loop is parallel to magnetic field. So this is area vector. Now magnetic field variation is given where B and T nodes are constant at time t is equal to 0. If the resistance of the loop is R, the heat generated in the loop after a long time t is equal to infinite. So we have to find total amount of heat, and total amount of heat will be solved using the integral, because we have to find total amount of heat, so we have to integrate it. And to calculate the heat, what we need to find, we need to find the power, then we can integrate it over limits of time. We can write that heat will be p dt integral 0 to infinite. This will be the amount of heat. So First, we need for that we need power, and for power we need induced EMF, because power is induced EMF, or V square by R. So induced EMF E will be minus d phi by dt, and it will be minus of d by dt of, suppose area is A, that is pi r square. So pi r square into magnetic field, that is B node E, minus T by tau. So from this, induced EMF comes out to be pi r square as it is, B node as it is, e raised to power minus T by tau, with differentiation of minus T by tau, that will be, we have already negative sign here. So it will be minus 1 by tau, minus minus plus, and we have pi r square B node tau e raised to power minus T by tau. That's the value of EMF, or induced EMF. Now from this, power will become, that will be V square, or induced EMF E square by R. So that will be pi small r square. Small r here represents radius, capital R represents resistance, B node by tau R. Okay, we have to square it. So pi square R4 B node square tau square, and e raised to power minus 2t divided by tau. So that's the power. Now we can integrate it to find the heat. So heat will be integral 0 to infinite p dt. Now out of power, all these terms, pi square r for b naught square tau square r are constant, so they will be outside of the integral. Pi square r for b naught square by tau square r, integral 0 to infinite e minus 2t by tau into dt. Now its integral will be r4 b naught square tau square r, integral will be as it is, minus 2t by tau, just divided by the differentiation of this part, that will be minus 2t by tau, with limits 0 to infinity. So this tau cancels the square, and we have minus pi square r4 b naught square divided by 2 tau r, with limits, that will be e raised to power minus infinity when we put infinite, and negative e raised to power minus 0 when we put limit as 0. So we know e raised to power minus infinity, or we can write it like this: pi square r4 b naught square 2 tau r, it will be e raised to power 1 by e raised to power infinity minus 1 by e raised to power 0. Now 1 by e raised to power infinity, as e raised to power infinite will be infinite, so 1 by infinite is 0, minus e raised to power 0 is 1, so 0 minus 1 will be minus 1, and as a whole this will give us pi square r4 b naught square 2 t r 2 tau r. So option B will be the right answer. Let's move to the next one. When a current in coil changes from 5 to 2 ampere in 0.1 second, average volt is 50 volts produced, self-inductance. So in this, we will use that induced EMF is equal to L di by dt. Induced EMF is 50 is equal to L. Change in current is 3 ampere in time of 0.1. We are taking positive signs only here. So it will become L will be 5 by 3 or 1.67 Henry. Now let's move to the next one. Figure shows a circular area of radius B, a radius R. So here in the figure as shown that in this region there is a changing magnetic field, and due to that changing magnetic field there will be induced magnetic field, and we have to find the value of that magnetic field, and we have to show its behavior, that how it will behave. So first of all, let's slide it down slightly. Now we know from Faraday's law that curl of E, or cross product of E, is given by negative of B by T. So as we know that this curl is I curly y curly x plus J curly y plus K curl y curl z of, now we will have EXI here, EY here, and EZ here, is equal to negative of derivative of B. Now it is mentioned that field is into the paper, magnetic field is into the paper, and it is changing at a constant rate. So the rate of change of the field is constant and is in the negative z direction. So this part, we can say right hand side is suppose minus c, or negative negative plus, as this direction is negative k, so negative negative k. C is the rate of change and k is the direction here. So this right hand side will be in the positive k, positive x, positive z direction. And how we can get positive z direction from this side of the expression? We can get it with I cross j, with cross product of I and j component, and with the cross product of, we can say, j and I component. So these two, from these two we can get the value in the k direction. Means the field produced here will be in the ex and ey directions. Now let's come to the shape of the this, we can say, area. Now suppose this is a ring. If this is a ring, we can assume it is a either it is a hollow ring or it is a in form of a disk. Now if it is a ring, then charge, due to magnetic field there will be EMF induced, and EMF induced will be along the circumference of the ring. And we have, if we have a ring with some charge on it, we have a ring with some, suppose some charge on it, then electric field at its center will be zero. And if we see any of the diagram, electric field at the center will be zero. In any of the diagram we can see that electric field is zero in at all of the diagrams. But as we move away from the center, and if we apply Gauss law, then at any point inside this ring, as all of the charge is outside of, on the circumference of the ring, at any point inside the ring electric field will also be zero. So inside the ring net electric field should be zero, and in all of the figures none of the figures show this type of behavior. Means this is not a ring, we can suppose it using a disk. So now we will solve it using a disk. Suppose we have a solid disk which has charge all over distributed across it, and in these type of scenarios we know that electric field inside is proportional to radius, uh, directly proportional to radius, and outside electric field is proportional to 1 by r square. So the diagram which best describe is option D for us. Now let's move to next question. Let me clear here again that changing magnetic field produces electric field, and we have to find out behavior of that electric field. Now behavior of electric field can be assumed by assuming that either it is a ring or a disk carrying some charge. Now if it is a ring carrying some charge, then field inside will should be zero, and none of the graphs shows that with distance less than radius r, field should be zero, and none of these show this. So we will go to the disk part, that it is something like disk, and charge is distributed inside also. And if charge is distributed inside, then for that, using this integral, that E dot ds is equal to q by epsilon naught, where q is an enclosed charge, using gas law, we can easily solve that inside electric will be directly proportional to radius, and outside it will be proportional to 1 by r square. And that is the curve relationship for option D. Now let's move to the next one. Here, coil of cross section having circular cross section having 1000 tons and 4 centimeter face area, placed with the axis parallel to magnetic field, which decreases by 10 raised to power minus 2 Weber per meter square in this time the EMF induced in the coil. So here axis, we can say axis of the coil is parallel to magnetic field. Means suppose this is our coil, then this will be the axis of the coil, and it is faced axis of the coil is parallel to magnetic field. Means angle between the area vector and the magnetic field is zero, so we will have the dot product will be maximum, and flux sorry EMF, that is equal to rate of change of flux, will be given by area outside, and inside we have a magnetic field. Now area will be number of tons multiply the area of one ton, so that is 4 into 10 raised to power minus 4 in meter square into 1000, and dV by dt is change in magnetic field is minus 10 raised to power minus 2, with time that is also 10 raised to power minus 2. So this get cancelled, and we have 4 into 10 raised to power minus 1, or we can say if we have to write it in millivolt, so this will be 400 into 10 raised to power minus 3, and it will become 400 millivolt. Option A will be the right answer. Let's move to the next one. A circular loop of radius 0.3 centimeter lies parallel to a much bigger circular loop of radius 20 centimeter. The center of the small loop is on the axis of the bigger loop. The distance between their centers is 15 centimeter. If current of 2 ampere flows through the smaller loop, flux linked with the bigger loop. So we have to find out the amount of flux linked with the bigger loop. Now let's draw this diagram first. Suppose this is our bigger loop and this is a smaller loop, and they they are on the similar axis, means their axis coincides, and this distance between them, distance between their centers is 15 centimeter. Now radius of smaller loop is 0.3 centimeter, or 3 into 10 raised to power minus 3 meter. Radius of the bigger loop is 20 centimeter, or 20 into 10 raised to power minus 2 meter. Now smaller loop does have some amount of current through it, and we have to find the flux linked with the bigger loop. Now flux linked with the bigger loop will be given by this formula, that phi big will be magnetic field at its center So B, suppose this is point O, this is point A, its center is point A. So BA into the area, oh sorry, BO, magnetic field at O into area of bigger loop. Now we have a formula for magnetic field at its we can say axial point due to a current loop. Due to this current loop, we can find magnetic field at point A, and due to this current loop, we can find the magnetic field at point A. But here it is given that current is in the smaller one. In the smaller one, we have given 15 ampere current, and we have to find the flux through the bigger loop. And as we know that for finding the flux, we need to have a fixed value of magnetic field. Now, at the center, we can calculate the value of magnetic field. Due to this coil or this loop, we can find a value of magnetic field at point O. But as this loop is quite big, so magnetic field's value at all the point inside the loop will not be same. It will be variable, and that for that we don't have any method for calculation. That we cannot calculate or we cannot find out an average value of magnetic field for this whole loop. So what we do, we reverse the condition. What we will do here, we will find amount of flux passing through the small loop provided current in the bigger loop. As this small loop is very small as compared to this, it is almost point size. This is of radius 20 centimeter and it has a radius of 0.3 centimeter. So magnetic field inside this loop due to bigger loop will be almost constant or approximately constant. So using that, we can find out the flux passing through the small loop, and we know that amount of flux due to on the we can say the amount of flux linked in both of these will be always equal and just opposite in direction. So amount of flux due to bigger loop in the small loop and due to smaller loop on the bigger loop will be equal and opposite. So we can do calculation for either of these and result will be the same. For bigger loop, we cannot do the calculation because here value of magnetic field will not be uniform. But for smaller loop, we can do calculation as this loop is very small, so value of magnetic field will be almost constant. So we have been given current in the smaller loop. We assume that same current in the bigger loop. So that 2 ampere current that was in given question flowing through the smaller loop, now we assume that it is flowing through the bigger loop. So flux of the small loop will be magnetic field at point A into area of the coil A. Now magnetic field due to this coil at point A is given by this relation, that as it is a we can say as this point is an axial point, so for axial point magnetic field is given by mu naught by 4 pi into 2m divided by the distance cube, and this distance is the this one. Let me draw. Where it is, I think, yes, now it will work. So this distance we have to find out, and this distance we can find out is Pythagoras. It will be 15 centimeter square plus 20 centimeter square. So here mu naught by 4 pi will be 10 raised to power minus 7 twice m. M is the magnetic dipole moment of this loop, and that is given by the current into its area. So current is 2 ampere and its area will be pi times r square. Its radius is 20 centimeters, so that is 2 into 10 raised to power minus 1. So it will be square of this. So 4 into 10 raised to power minus 2 divided by the distance cube, and distance, that this is the distance. it will be under root of 15 square into 10 raised to power minus 4, that is 15 centimeters square, plus 20 centimeters square, that will be 20 square into 10 raised to power minus 4 power cube. Multiply the area of the smaller loop, that will be pi, times its radius square, that will be 9 into 10 raised to power minus 6. So what we will have here, we have 4 into pi, 4 into 4 16 into pi square, so 16 pi square into 9 into 10 raised to power minus 7 minus 2 minus 9 minus 6 minus 15 divided by, so this will become 16 pi square into 9 into 10 raised to power minus 9 minus 15 divided by 15 square 225 plus 400 625 into 10 raised to power minus 4, so 625 into 10 raised to power minus 4 power under root of and cube. So further we can write it like pi square will be 10 almost, so 16 into 9 into 10 raised to power minus 14, 625's under root will be 25, so 25 cube we have here, and 10 raised to power minus 4's under root will be 10 raised to power minus 2 into 10 raised to power cube of 10 raised to power minus 2's will be 10 raised to power minus 6. Now this is 14, so solving this we will get 0.0088 into 10 raised to power minus 8. Now we can further write it like 8.8 into 10 raised to power minus 11. And the most nearest possible that match is with this question, that is option A, that is 9.1 into 10 raised to power minus 11. So that will be our answer for this question. So with this, we end this video here. Again, if you have any doubts or suggestions, you can put them in comment section. I will try to resolve them. And if you find this video helpful, useful, then do press the like button, share it as much as possible, and subscribe to our channel. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.